Hi there, today on the bench another LCR Tweezers meter, the ZOYI ZT-MD2, sent in by Banggood for review. I did not pay for it, so I mark it as promotion, but you know that doesn't stop me from giving you an unbiased review. As seems common, the tweezers come in a nice case. Inside is a manual, a USB-C to USB-A cable, and the tweezers of course, which are quite difficult to extract from the foam molding. Once out, I have to say I like the all-metal casing. Rear sports this strange warning. I get the part about the voltage because this unit can actually measure volts, but the rest seems a bit ridiculous. Maybe an attempt to get out of a warranty claim? I claim professional status and power it on, and it starts in volts mode. I do like the display, large numbers, easy to read. Except for the voltage icon showing a battery light gray on dark gray, the camera picks this up far better than the human eye. It is largely invisible. Who came up with that color scheme? Let's try measuring a battery. Whoops, I accidentally did a short press on the power button, which activates the hold function indicated by the H on the right side of the display. Let's unhold, and 8.25 for a rechargeable 9-volt battery is more like it. Note the display also shows the latest high and low values. These can be reset with another button. The hardly visible icon shows the polarity relative to the tweezer arms. If I reverse the battery, the icon reverses as well, provided you can see it. For another test, I put the tweezers in auto mode. It reads a precision 10K resistor spot on. Another precision 10K resistor. And a 25K precision resistor. A 10 nanofarad 1% cap is correctly identified and displayed. And so is a 20 nanofarad capacitor, a 1 nanofarad 1% capacitor, and 5 1 nanofarad capacitors in series, which should be 200 picofarad. Electrolytic caps now, 10 microfarad is no problem, but 2000 microfarad is shown as a voltage, because of the dielectric absorption that makes capacitors sometimes generate voltage out of apparently nowhere. I need to select the capacitance function instead of auto. And now it can measure it. Back to auto and trying to measure 1 microhenry. That one fails too, but this time because the tweezers identifies it as a very small resistor. Changing the function to inductance should fix this. And indeed, it now shows about 1 microhenry. These are 10% parts, so the value is not exact. Measuring the other inductances in my test box works fine without problems. Measuring a single silicon diode works fine with the tweezers indicating the direction of the diode using the nearly invisible diode icon. This color scheme is ridiculous and spoils the whole thing. Maybe the icon color can be changed in the settings, or maybe there's a new firmware that fixes this. Let's have a look at settings. The usual things like language. The ZT-MD2 can reverse the display for left-hand use. Nice, a capability that's sadly lacking in my Firmware tweezers. Other maybe interesting settings are the auto power off time, the measuring speed. Although the manual doesn't mention it, I assume that, like with many meters, slow gives a better accuracy and a more stable readout, so I leave it on slow. Even at slow speed, the tweezers are responsive enough. Model defines whether the LCR measurements are modeling a capacitor as an ideal capacitor with an inductance and resistance in parallel, or with those components in series. There are similar models for inductors. Auto lets the tweezers choose the model. Par selects what additional parameters are displayed. Z the impedance, X the reactance, or P the phase angle. Again, auto lets the tweezers select the additional parameters. Function allows to disable some of the functions of the tweezers, for example to remove the signal generator. Calibrate allows a recalibration using a short, open and a number of precision resistors. Restore is for setting the tweezers back to factory defaults. And lastly, About shows the name and firmware version, in this case version 1.2.4, which happens to be the latest version according to the ZOYI.co.uk website, or so I thought. No settings to change colors and no new version, but the manual says that you could change the color scheme. The ZOYI UK site does not have any tools for that, so I searched the internet and I found a nice Python utility on GitHub, which looks straightforward to use. Basically, it uses the USB connection to get and send color information using hex notation, red, green and blue, and each can be a value between 0 and FF. So 000000 would be all black, FF all white, and FF0000 would be full red. You get the idea. Let's use it. The tweezers are connected using the supplied USB cable. I speed this up a bit. First, let's do a dump of the existing color scheme. That works fine. I think the setting I need is FG_type or BG_type, with FG obviously standing for foreground and BG for background. Let's change the background to white. Okay, it did not like that because I forgot to add the -- in front of the BG type. Easily corrected. And the effect is instantaneous. Much better. But I guess it could still be improved. Here you see what I finally decided on. The first line changes the foreground to yellow while the background is back to what it was originally. Then I decided to make the background black. The dump command shows that the tweezers slightly modify the RGB values, so instead of FFFF00 for FG type as I selected, it uses F8FC00, but that's close enough. This is how that modification looks. Here's a repeat of the diode test, but this time with a new color scheme which makes it easier to see. Note that quite understandably, diode test for silicon diodes stops working if the voltage is set to 0.3 or 0.1 volts. For the same reason, it cannot measure multiple diodes in series or LEDs. If a diode is shortened, you get a beep and this symbol. It still beeps with 1 ohm and 10 ohms, but not with 100. You can use this mode for continuity test as resistance mode has no beep. I think the new color scheme works great and I like the looks. Of course, colors are a matter of personal taste. Now, Python and command line isn't everyone's cup of tea either, and so I searched further for a Windows program doing this. And I found this site called ZOYI Tools, and it appears that this site is slightly more up to date than the ZOYI UK site. It has the same user manual but an updated 1.2.5 firmware and 2 software downloads, one for color change and one is a Windows program probably allowing some sorts of remote control, which strikes me as strange for tweezers. I am very reluctant to run downloaded Windows programs, and my only Windows machine at the moment is an ancient Windows 7 laptop, so I use VirusTotal to see if the color changing tool called color version 1.0.4_en.exe is clean. That might just be a false positive, given that so many other AV tools did not flag anything. But since I already changed my color scheme and the Python version is just 173 lines and easy to understand, I think I skipped that Windows version. Moving onwards to the LCR program. As you can see, that consists of an executable and a bunch of DLLs. I actually tested each one with VirusTotal and they were all given a clean bill of health. This here is the main program as a sample. Yet I decided not to try this, as this is a review of the tweezers and not some Windows program. So onwards with that. There is a new firmware, 1.2.5, while I have 1.2.4. No information what has changed. According to the manual, holding the fourth button while powering on brings a bootloader and a USB drive appears on the PC. Yes and yes, but as soon as I let go, both disappear. In the end, I resorted to keep the power button pressed and copy the new binary into the USB drive on the PC. That seems to work, but it goes so fast that I show this in slow motion. And going to the settings menu confirms that I now run 1.2.5. To be honest, I have not noticed any difference from before, and the update also preserved my changed color scheme. Let's dig a bit deeper. Here is the waveform when set to 1 kHz and 0.6 volts. Incidentally, the display shows 10 megaohm, which is the impedance of the scope probe I connected to the arms. No issues here. 0.1 volts is fine too. Let's change the vertical resolution to make the signal bigger. 0.3 volts is the last choice you have on signal amplitude, and this is fine as well. Going back to 0.6 volts and changing the frequency to 10 kHz. No problem here. Note that the impedance of the scope probe shown is dropping as expected with higher frequencies. 100 kHz now, which is the highest supported value, and there's not much left of the DC 10 megohm impedance of this probe, but the tweezers are working just fine. 100 Hz now, and we are back to megohms. Same of course for 120 Hz. And back to 1 kHz. The tweezers has a very nice scan function where it cycles continuously through all 6 frequencies, so you can see frequency dependent effects directly, here for resistance. Here's the same for a 10 nanofarad capacitor, CS standing for capacitance in the serial model and CP for using the parallel model. D is the dissipation factor, the reciprocal of Q, the quality, so lower D is better. For a good 10 nanofarad capacitor like this one, there's not much going on. But the results for a 100 microfarad electrolytic cap change quite dramatically with the frequency. CS drops from 100 microfarad to about 10, but CP is really nuts when using 100 kHz, which is why LCR measurements are so easy to get wrong. I measure the accuracy of the voltage measurement using my data precision 8200 calibrator, and I noticed that when exceeding 16 volts, the display turns red. This serves as a warning, as the tweezers can measure only up to 32 volts and will get damaged if you exceed this. When it turns red, you are halfway there. The accuracy of the voltage measurements is okay. In my tests, it was always just one count too low, which is what causes this drop of the graph at the millivolts. But since accuracy is specified with ±2 digits, it is fully in spec. Capacitance is pretty accurate. I only tested 1 kHz. As you can see from the specification, that gives best accuracy all around. The big deviation on the right are electrolytic caps, which not only have a large tolerance, but also are not long-term stable in their value. Even with that, the tweezers stay well below the 5% spec for that range. My toolset is a bit limited in verifying inductance, as I have no good quality large inductors for testing. So this graph here does not go any further than 1 Henry, but the tweezers did a pretty good job at all inductors I threw at them. Lastly, resistance, and again the tweezers are pretty accurate. No complaints. On the right side, the accuracy for the range from 1 meg to 10 meg is only 5%, and that is certainly okay. On the left, below 1 ohm, I thought the tweezers did not have rel, so contact resistance is causing issues here. But as you can see from the spec, this range is anyway outside the specified accuracy. It turns out the meter does have rel. It is called tar in the manual, but I continue to call it rel. I'm measuring a 0.5 ohm resistor here. A long press on the second button engages the rel, and there are now just a few milliohms left. Sadly, there's no indication that rel is active. Measuring a 1 ohm resistor now, and as expected, we are just seeing about 0.5 ohm. So far, so good. The trouble is that the manual says nothing about how to turn rel off. Turning the tweezers off and on, and measuring my 0.5 ohm resistor, no, rel is still active. Changing the function, no, rel is still active. The only way I have found is to shorten the tweezers, which of course should now be minus 0.5 ohm, and activate rel again. That's a pretty windy way, and depending on contact resistance it might not be exactly 0, so all your resistance measurements are now slightly off. I sent a message to ZOYI asking about that, and I will update the video description if I hear anything back. By the way, the manual seems to indicate that there's a rel for capacitance, but pressing rel did not do anything in that mode. There is a signal generator on board. If you wonder about the skewed square wave, that was my mistake of having the scope in AC mode at such a low frequency. Changing parameters with the 3 buttons is very convoluted and involves a choreography of longs and short presses, not something I want to do often. The waveforms seem to be upside down, but that's simply because I connected a scope probe that way to the arms. Reversing the arms makes the waveform appear closer to the display, but these are all AC waveforms, which means they are not really half or full rectified sine waves. I question the usefulness of these, and quite honestly of the whole signal generator function. I think I will turn this function off in the settings, but that's just me. Other folks may like this function. Another feature is sorting mode, which you get by long pressing the 2 middle buttons simultaneously. In this mode, you have to set a target value and a tolerance, and if you then measure resistance, for example, then the tweezers will tell you whether they are within or without. This is a useful function sometimes, but again, the user interface for setting target and tolerance is so convoluted that I'm sure I will never use it. Anyway, since the default for resistors is 1K and 5%, let's test some resistors. Okay, you can see if I select some 1K resistor, it calculates the error percentage against the target and compares that with the specified tolerance. And if it's within, I get a single beep and a green pass. If I measure a 2.4K resistor that was at hand, I get a fail and 2 quick beeps. It also works for capacitors and probably for inductors, but I haven't tested it. The default target is 1 microfarad, and my test capacitor with minus 4.2% just passes, but a 2 microfarad capacitor of course not. While playing with this, I encountered a problem in that the third button from the right was stuck. I could no longer change the voltage. It works again if I loosen the screws that hold the housing together. But as soon as I tighten them, it jams. The housing is held with 3 machine screws, no self-tappers. The lithium battery is wrapped in plastic and just lying on the components. The battery leads are soldered in, and the battery is marked as 300 milliamp hours, 1.1 watt hour. The metal buttons live on a common elastic strip that makes them bounce back after presses. I examined the buttons and the 2 housing parts for any roughness or scratches that could make a button jam, but I did not find anything. And if you wonder, the actual switches on the PCB work fine. In the end, I applied a little WD-40 lithium grease with a cotton bud on the openings for the buttons, and that seemed to have done the trick. So, what's my verdict on the ZT-MD2 compared to the Firmware LCR ST1? They are both competent LCR tweezers, but the ZT-MD2 has a few things that the LCR ST1 lacks. It can do 0.1, 0.3 and 0.6 volts, whereas the LCR ST1 only offers 0.3 and 0.6 volts. The ZT-MD2 has 6 frequencies going all the way to 100 kHz, while the LCR ST1 has only 3 and ends at 10 kHz. Then there is the scan mode of the ZT-MD2, which I really like. Apart from that, the ZOYI has a larger display and font, and the display flips if you use it in the other hand. So in my opinion, the ZT-MD2 is the winner. Thanks again to Banggood for sending it in, and I leave a link in the description of the video. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.